Right, so good morning, and for those of you who may have endured 3 talks from me yesterday, I don't know whether anyone's done that full, thinking of having an award tomorrow because there'll be a 5th one tomorrow. Anyone who's actually sat through all 5, I'm kind of still trying to think what the prize is going to be, but I am talking on a different topic today from yesterday, where there was some overlap between the micro apps talk and the Mimic closing session talk last night. I will not be talking about the LMBA this morning. In fact, this is really a bit of a sort of a revisit, in actual fact, to a subject that probably I wouldn't be surprised. I think I was talking about maybe 2 to 3 years back at these kinds of events. And as is often the case with these relatively new, novel ideas, approaches, techniques, they don't usually go down very well straight away. You know, people don't all jump up and down and come and say, oh, wow, that was great. You know, they kind of all sort of just disappear slowly, and you think, well, okay, cheerio, thanks for listening. That's sort of what happened on this, as indeed 5 or 6 years ago happened with our continuous modes. I see the Cardiff team the Cardiff Mafia sort of stuck at the back there. I don't know, can't see the rotten tomatoes that they are now. I know they've got them in there somewhere, but in fact, this is what we certainly Paul, Professor Tasker, and I seem to have almost taken on as a hobby, really, which is waveform mathematics, waveform engineering. I think was his term, and I guess I got induced into this fascinating activity, and it is quite mathematical, but I think it does quite a lot has come out of it in terms of design, particularly harmonic designing, harmonic matching for PAs. So this is going back a little bit, as I say, to some work that we probably have presented in the past. Now, this may appear to be a thinly disguised bit of bragging, so why don't I just simply throw away the disguise and have a good brag? One of the reasons we thought that there's been renewed interest in this paper, which we published, as you see, a couple of years ago, 2.5 years ago. It appeared in the Transactions, IEEE Transactions. Continuous mode power amplifier design using harmonic clipping contours, theory and practice. In a sense, I'm not sure is that good of a title in retrospect. I think that what we're really simply doing here is extending the concept of continuous modes from reactive second harmonic terminations to include terminations that may be sort of anywhere on the Smith chart, to say include resistive as well, using sort of the same mathematical approach, this zero grazing waveform mathematics. To my utter surprise, I have to say, it received the IEEE Microwave Prize for Best MTT Transactions paper in 2014. We only found out it because it takes them a couple of years to figure this out. This was only awarded at the IMS this year in San Francisco. And so that was, in fact, very rightly so. Tim Canning was the lead author. He was my PhD student, and is now currently working. He's not here by any chance. I haven't seen him here this week. He is, although from Northern Ireland, he is actually now working for Infineon in California. So as a result of this, there has been, I've received quite a lot of emails from all quarters, about this paper and so on, and people don't really seem to understand it all that well. And I must admit, picking out what is a fairly old set of slides, I must admit I was having a little bit of trouble understanding it myself. But anyway, here we go. The idea here is to revisit this subject. That's the idea, right? And so therefore I'm going to have to move fairly quickly. I mean, because as I say, really this paper was simply an evolution of our sort of older work on Class J and continuous modes. I feel it is, to sort of get the continuity and to try to understand what this sort of most recent evolution is all about. I think it is really necessary just to take you through what is, almost now a standard tutorial that probably a fair number of you may have seen either me doing or even others. So we will just sort of revisit, revise really, Class J concepts, what we call continuous modes. This PA waves postulator, if any of you have been to my PA courses with CEI or Besser Associates, you get a copy of that, also with the book as well. Then rather quickly, I'm not going to dwell too much on the design example. Really the meat of this is moving into this more general formulation, which enables us to formulate a much clearer picture as to what our design is likely to be doing, taking consideration of particularly second harmonic terminations. I stuck this slide in at the first, in fact, just to sort of, in a sense, reinforce what I was just saying before about, particularly, I think, Paul and myself, almost sort of, I would almost say it's almost like a hobby, really, it becomes, messing around with these waveforms. We both do it. I think we both enjoy doing it. And I certainly find a lot of my best waveform mathematics work gets done on aeroplanes and long journeys and so on, usually to the considerable sort of amazement of whoever it is sitting next to you. You know, you're sort of doing all this trigonometry and sort of stuff. I think really what it's all about is, I think what just is an unsatisfactory aspect of our mathematics. It's somehow or other, you know, you take a sine wave, obviously, you know, you start off with a sine wave, and you start adding, you know, harmonics. I've just here added, almost at random, a bit of second and a bit of third, more or less random phase. And of course, what happens is the peaks and the dips change, you know. And when you're designing amplifiers, of course, you're particularly interested in the minimum point. Obviously, if this minimum point crosses zero or tries to cross zero, you're sort of in trouble. And that is the fundamental philosophy behind really what I'm talking about today. You know, we know that we can get some benefit in terms of power and efficiency by engineering waveforms that have some harmonic content. However, you can't just simply sort of add harmonics at random because in most cases, you start adding harmonics at random, you will end up with a waveform that drops below zero. And so really, it to me has always been a frustration that, you know, you express this waveform in harmonic form, you know, V1 cos theta plus V2 cos 2, you know, plus, you know. You do that and you say, well, okay, where are the peaks and the dips? Now, of course, I go back to, I mean, I did differential calculus when I was 13, I think, back in those days. So, you know, you sort of think, oh, yeah, well, you differentiate it, right, and set it equal to zero. And, of course, you get this humongous trigonometric equation that has a million solutions. And that just doesn't seem to be the right way of finding out where the peaks and the dips are. So that's really, to some extent, I think, the sort of one of the starting points of all of this. You've got to sort of try to take a different angle on attacking this problem. And it is sort of a piece, it is a mathematical process, really. Determining the maximum and minimum points given a waveform in harmonic form is a surprisingly difficult task. And as certainly amplifier designers, a key feature is that the voltage will not reach zero. That in itself is a somewhat debatable subject when it comes to efficiency. However, let's not get into that just at the moment. So I realize I probably have to move on a little faster than I am at the moment. So I'm going to really try to scoot through this class, as I do want to leave myself enough time to talk about the real more meaty subject. This is, you know, we start off with a Class B current waveform. We all know that gives us an advantage of pi over 2 over a sine wave. So, you know, you play the devil's advocate and would say, well, okay, why don't we do the same thing? Why does nobody do this, you know? Why don't we do the same thing with the voltage? Because then we'll get another pi over 2 benefit, and we'll end up with an amplifier with pi squared over 8 efficiency, which of course is somewhat troublesome because it's considerably greater than 100%. I haven't really got time to start making jokes about the Arkansas State Assembly that actually voted some years back that the value of pi is 3. But even if you are in Arkansas and you take the value of pi as 3, you're still in trouble. Anyway, okay, I haven't got all morning here, so I better move on a bit. You can resolve this. Essentially, what's happening is that the device is absorbing energy. To make those waveforms work, you have to feed in second harmonic, something which incidentally we have done at Cardiff quite successfully, as indeed has Zoya Popovic involved quite a few papers on that subject. That's a separate subject. essentially, you have to recognize that. And so moving into what we call Class J waveform, what we do is we resolve it by shifting the phase of the voltage waveform by 45 degrees. When you do that, then the second harmonic impedance is reactive, which is actually rather good. If you do it the right way, it actually becomes capacitive, and guess what you've got on the output of every RF power transistor is a larger capacitor than you care for, so that's really rather convenient. So I'm going to sort of move on a bit. I mean, essentially, the Class J concept is the use of this reactive termination rather than having this short circuit, which is the sort of the traditional approach to designing Class AB amplifiers. So I'm moving along reasonably quickly here. This is your PA waves little sort of sequence here, where we add some second harmonic. That's going from the sine wave. We're just adding second harmonic. In order basically to do that, it turns out that we can actually increase the fundamental component up by this factor of the square root of 2 by adding this sort of 0.5. This is normalized to the DC level. And so this is just doing what I've just done with the Class B waveforms, but doing it with only second harmonic. But the key thing here, this little program PA waves, it tells us that we have got a negative resistance termination. I used to call this a postulator. This is where we're actually sort of going to the device plane and forcing the waveforms that we want, and then the program tells us what impedance we need to present to it. I must admit, I was talking with James over there about this the other day. Strangely enough, it has always seemed a very logical thing to do to me as a circuit designer. I've always actually had a certain amount of difficulty selling this concept of designing things this way around. But anyway, there we go. This is the beginning of the thing. Obviously, we can't have that, so we have to shift the phase by 45 degrees. That brings in this factor of square root. So the square root factor of 2 that we gained initially in power and efficiency, we now lose because of the phase, the phase angle, the cosine of the square root of the 45 degrees gives us that square root of 2 factor. So the interesting thing is, you see, we're back to Class B efficiency, but we have this range now of second harmonic and fundamental impedances. We have these pairs of impedances that will give us the same power and the same efficiency as we think in traditional terms, we only got at this single point where we have the short circuit. So this is what we have. I think Paul invented the term, I think, was design space, which I think is a very good way of describing it. This incident, there was one or two little side issues about Class J, incidentally. This peak clipping, this is something that another my Cardiff colleague Roberto over there on the corner, we've been spending a lot of time on this. With gallium nitride transistors have this very, very extended knee region, and this business of the clipping of the current when the voltage drops into the knee, back in the old days of gallium arsenide, you could almost get away with this. You could sort of say, well, we won't let the voltage drop into the knee. You wouldn't actually lose all that much efficiency with that little bit of voltage that you want to keep the device out of its knee region. I'm afraid that just goes out of the window when you start working with LDMOS or indeed with GaN. But it is a significant effect. But in fact, the Class J waveform tends not to clip the current in quite such a disastrous way. But anyway, that's a little bit of a sign. So, you can get values for these various components and you can design circuit. I was always quite pleased with this simulation. This is a simulation using a real transistor model. And, I was always quite pleased with that the voltage and the current waveforms really do actually match up quite well with the very much more idealized calculations. Okay, so that works quite well. Basically, what we're talking about here is design space, as I say, and I'd illustrate that with a couple of Smith chart plots. This is my sort of idea about how the traditional design, if you're going to try to design a Class B type amplifier, deep Class AB we normally operate in, the traditional view would be you'd have to do something like this. You have to somehow, over your bandwidth, you have to preserve your impedance somewhere in the vicinity of your load resistor, your load line. And I'm showing here a kind of a Chebyshev kind of a thing, I used to show how this all fits in quite well with synthesis. We're going to hear more, I think, from Peter later on about that. synthesizing networks. You know, this is a sort of a Chebyshev, this is the sort of the footprint of a Chebyshev network, that you can sort of wrap your impedance trajectory around the point that you want. But then you have to do the same thing with your second harmonic, and that turns out to be quite a lot more difficult as the bandwidth increases. And so really what we're saying here is, yeah, well, in actual fact, you don't actually have to do that. It turns out that continuous modes give you this more extended range. What I'm showing here are the extreme ends of what we now call this continuous modes. The class B, what I'm showing is the fundamental impedances are in blue, and the corresponding required second harmonic impedances are in red. So what we've done so far is show that there is another pair of sort of points in this impedance space that will give you the same performance. But there is, of course, as you vary that second harmonic, there is this continuum, hence the term continuous modes. This all started, and again, I can go into stories about where I was and how much I'd drunk when I noticed this the first time. We haven't got time for that this morning. Basically, if we write the class J expression with the second harmonic term that we've just sort of derived, basically, you know, we've got this quadrature sort of component here at the fundamental and this second harmonic term here. The amazing thing was that it factorizes, and this was really, this equation here was really the start of the realization that we can solve this problem, the trigonometry problem that I started off with. We can sort of rather elegantly bypass the need to differentiate things by simply starting off in the first place with an expression for the voltage that does not cross zero. If we express the voltage as a product of factors of this kind, all of which are above zero. These are sort of non-zero crossing functions. And so if we sort of basically specify that whenever you make a power amplifier, if you just simply multiply expressions of this kind together to build up a series of harmonics, you will end up with a waveform that grazes zero, maybe in one or two places, but does not actually cross zero. And that is really what this is all about. And so then, I'm not sure Paul and I have ever quite agreed. I think we both went on a flight to San Diego, and we sort of met in the hotel bar, and we both sort of opened our notebooks and said, oh yeah, here we got, you know, we introduced this term beta, or of course Americans say beta, and that is a very neat way of defining this whole family of waveforms, which are shown here. This has appeared in various places, and in fact I have very confusingly made the parameter here alpha. At some point along the line, alpha evolved into beta. I'm not quite sure why, but anyway. So that's the family, and this is the design space, which is shown here. And of course, in fact, the design space extends the other way. We sort of tend to prefer always to present this with the second harmonic impedance down here in the capacitive side of the Smith chart, simply because transistors have output capacitance, you know, so that's jolly nice. But in actual fact, of course, this design, this range of second harmonic impedance that you can basically still, by arranging to have the correct reactive component at the fundamental, you can maintain maximum power and efficiency over this quite a wide range. And in fact, interestingly enough, if you go back into sort of class AB mode where the second harmonic is lower, you know, you can actually even extend this even further. You know, this red line, it really goes, you know, sort of 2/3, 3/4 of the way around. So that's the sort of conventional mode. This is rather an old plot. This is Peter Wright that some of us will remember. Not here, is he, Peter? But this is one of the first amplifiers we were making quite high efficiency. I must admit, sort of implied this a little bit with some of the results I was showing yesterday. These days I tend to get slightly embarrassed showing some of these things. It's not a bad result, actually. But this is a very, very friendly transistor. You know, I think that I always think, you know, you'd better be doing 70% over, if you're claiming, you know, oh wow, you know, we got octave band, all this sort of stuff. You know, if you're only getting 55% efficiency from this transistor, I'm afraid, you know, you've got a bit of work to do. So anyway, there we go. That's the sort of that's the situation. We call this the class BJ modes, continuous modes. However, okay, so this is now, how's my time going, Malcolm? Here. Oh, okay, right, that's about right. Okay, that's fine. I thought when you showed those cards, they were kind of marks. You know, you're going to sort of, you know, put up, you know, you put up a 1, it's saying, hey, come on, this is getting a bit boring, you know. Right, so this is where things get a bit more tricky, all right? So you've got to just sort of take a sip of coffee, and so have I, actually. I've got to concentrate a bit more, too. It's a while since I presented this. The problem here is, you see, that we are, of course, this is all very fine and good, but there are two very big problems, actually. It's very good, I mean, okay, they're not fatal problems. There are two problems. One problem is that in practice, when you design a circuit, it is extremely likely that the second harmonic will drift inside the Smith chart. In particular, for example, if you're going to greater than octave bandwidth, for example, you know, obviously you're going to have to sort of, you can't be in two places at once. You know, I mean, you obviously want the sort of the fundamental to be sort of doing something vaguely in this region here, but then by the time you get to the second harmonic band, you want it all to kind of sort of suddenly whiz out to the edge of the Smith chart. That's quite difficult to do, although if you saw a couple of my talks yesterday, push-pull is a way that you can do it. You know, that's one of the reasons that this work we did on continuous modes sort of drove us into doing, looking seriously at push-pull circuits, because push-pull circuits do, in fact, enable you to do this. You know, if you design the balun correctly, you can actually sort of independently match the fundamental and the second harmonic. They're no longer coupled together by the matching network. However, that has its own set of problems, in all honesty. And so therefore we thought it was indeed time to tackle the problem. Can we take this concept further? You know, can we build on this sort of mathematical trick that we seem to have, you know, as I say, this factorization thing, can we somehow extend that to include, to create these non-zero grazing waveforms that actually sort of display a resistive component at the second harmonic, which is what we're going to have in practice. It seemed to be quite an important thing to do. And in fact, this did indeed occupy me for many train journeys and many aeroplane flights. I think I have sort of, shown some of these guys my notebook. My wife calls it my sum book, where I'd been trying many different ways of doing this. It does get more complicated. In fact, I know Paul and I had a discussion about this. It's sort of like, you know, there comes a point where if the mathematics gets too difficult, is it really worth doing? I mean, this is, you know, sort of, but I suppose being a, you know, a bit of an old codger, and having done my PhD working for a mathematician and working particularly with Professor David Rhodes at Filtronic for some years, I still am very much a believer in trying to solve these problems analytically. I think it does give you more insight, even though, of course, you can just crunch the numbers on a simulator. You know, I mean, any old fool can do that, right? Sorry. So, as I say, to cut quite a long story short, and really I'm just playing for time here to make sure I say the right thing. This is the way we formulate the problem in order that we end up generating a resistive component at the second harmonic, but at the same time maintain this sort of positive, definite, the mathematicians use this term, you know, we've still got a 1 minus a cosine times a 1 plus this beta is still going to stay less than 1 magnitude. So those two curly brackets are still maintained. As I say here, it generates a, maybe I better just read my bullets actually, I'll get into trouble. This generates a set of zero grazing waveforms. That does include cases of lower than optimum power. That's to say we're not constraining the fundamental impedance to be at its optimum value, and also we will, when we multiply all of this out, we will also get second harmonic impedances that have both reactive and resistive components. So that this formulation now allows the designer to quantify the impact of what are called near misses on the fundamental and harmonic impedance targets. And so what basically what I have to do is to multiply this thing out. So you definitely need to know your trig identities, which the average undergraduate these days does not seem to know. Well, it depends where they come from, actually, without mentioning any particular parts of the world. There are some parts of the world where they definitely do seem to know their trig identities, and that's not the UK. But anyway, let's gloss over that little controversial matter. And So you can see it does start, see, this is where people kind of put off, you see. This is the trouble. So far, so good, right? But the actual process now does get a little bit involved. I mean, essentially, what we're doing here is comparing coefficients. So we're going to say, well, okay, in harmonic form, what we now want is a voltage waveform that has got these characteristics. That's to say, it's got fundamental, both reactive and resistive component. That's hence the R and the Q subscripts, and also the same thing at the second. That's what we want, is a function that when we multiply it out, does that. So we've got that function, which has this additional, very desirable property of not crossing zero. So it is really a matter of thrashing through your trigonometric, stuff. I incidentally don't even find the Mathematica type programs terribly useful for this. They get they get even more confused than I do when trying to do trigonometric expansion. But anyway, we compare coefficients. I actually, in a way, compare this whole process to filter synthesis. We're doing a similar kind of a thing here to what people who design filters do. They come up with this abstract mathematical function that is the sort of represents the filter response that they want. And then they start sort of, making circuits and deriving expression for the transfer characteristic of the circuit, and you compare coefficients and, outdrop your circuit values. I always used to think it was a very elegant business, and that's sort of what we're doing here. The problem is here, having reached these expressions for having done that process, we've now got these three parameters that are themselves sort of rather abstract parameters. And what we need to do really is to try to break them down to one parameter. What we're saying is, supposing we have knowledge of what our fundamental impedance is, and this is the way we usually operate this whole sort of piece of mathematics, and I have it on a spreadsheet, which I hope I'll have time to show very briefly. But the basic idea here is, well, okay, let's put a spot on the Smith chart. We have reasonable control, we think, of our fundamental impedance. It's a matching network, and we're pretty confident we know what the fundamental impedance is. All the way along, I'm assuming that current remains constant. That's a bit of a dodgy assumption, especially with gallium nitride. I'm having a laugh here with Roberto because we have been revisiting this in this respect just in the last 12 months. But anyway, more of that tomorrow, actually. But anyway, this is sort of what we really want to do, is to say, well, okay, we know what V1R and V1Q is. So therefore, it turns out that we can eliminate two of these three slack variables if we're good enough at mathematics. I had come close to doing it, but I never actually managed to get there, and I do sort of still greatly credit Tim Canning for doing this. He actually cracked this with, I think, a bit of help from Mathematica, I think. He kind of did a little bit of cheating, but anyway, we did manage to crack the maths. And as a result, what we can do is, this is really what I'm saying here, if we decide we know what the fundamental impedance is, what we can do is end up with a contour of places where the sort of the zero, we can plot the zero grazing contour. The contour where our waveform actually has this zero grazing contour is a line that we can plot by sweeping this one remaining slack variable. And this, I think, is the bit where people get a little bit lost. And as you can probably gather, I'm having to concentrate a little bit myself. That's what these contours actually are. And essentially, it's a demarcation line, because one side of the line, you're out of luck. You're going to be clipping and so on. The other side of the line, you can be anywhere the other side of the line, and you can do okay. And your power and your efficiency will be the same. So that's really the key point. And so what I've got here is, this is in fact a spreadsheet that does this. And I don't know whether I'll have time to show you a couple of examples of this. But for example, if you go back to basics and say, well, okay, let's just simply, let's assume the Smith chart is normalized to the RL, to the load line resistor. So we're actually at where the X is, all right? X marks our fundamental impedance. What those equations do is you end up sweeping this parameter, and you get this green area is okay. The green area to the left of this is the demarcation line here, and to the left of that line is okay. which is not so good. I mean, this to me in itself, although it's not quite as nice, it's not kind of an interesting plot really, it is nevertheless quite interesting because this is saying that the traditional view that you terminate the fundamental with the load line resistance and you short circuit the second harmonic, that is the only point, that will work. You know, anything else will not work. Any other second harmonic impedance, even if you have a short circuit stub or something like that, you know, you drift away from your short circuit over quite a narrow bandwidth. I think I have a slide showing that next. You're already moving into the clipping zone, and your power will go down. Your efficiency may not go down, but the power will definitely go down. So that's interesting enough in itself. But then, yet more quantitatively, we can now say, well, okay, if we say back off 1 dB, this is the 1 dB contour, so we sort of say, well, okay, let's just give a little bit here. Let's say, well, we're going to design a broadband amplifier, we're not going to get the optimum at every point. Okay, yeah, right. So that's okay. I'm probably not going to have time to show you the spreadsheet that does this, but these are, you know, freeze frames from a spreadsheet where you can literally dial these things in. But the interesting thing is, you see, you back off just 1 dB in terms of your, you know, so that in other words, you're giving the voltage a little bit more room. You know, we're not saying full voltage swing, we're saying, well, you know, 1 dB down the full. All of a sudden now, these equations are telling us that we have this very much larger area, you see, the sort of the acceptable range of second harmonic impedances suddenly sort of floods. You know, we got this flood of green moving in very quickly, and this, I think, sort of is telling us that, you know, it's sort of, you know, it's giving us some quite useful quantitative information. Essentially, we can now design a circuit with, so long as our second harmonic falls somewhere in the green region here, we're okay, you know. I think that's quite useful, being a designer. In fact, it's so useful that I think some of the software vendors ought to incorporate this. You know, but they never do. They never want to do that. You know, you start getting all sorts of interesting shapes. You know, this is where we actually go to the class J point, or you know, that's the where we're actually got a reactive termination, or the reactive component, the fundamental, and still quite a large area. As we approach the singular point, because remember David Rose was always very keen on his singularities, as we approach the singular point, which is the sort of the class J condition, we get this smaller and smaller, you know, we're sort of homing in on the extreme end of the class J point there. So I hope this has given you some idea of what this is about. Obviously, I'm sort of running out of time. This is an example of a particular circuit, how you might employ this when you're designing a circuit. You know, the standard, you know, kind of textbook approach to designing a parameter was to use a short circuit stub, right? We'll short the second harmonic. So this is a short circuit stub at 1.5 gigahertz. So you can sort of say, well, immediately you can say, well, okay, we'll back off this resistor a little bit. You can see I've sort of said, well, we're not going to make it actually the RL. We'll back it off just a little bit from the RL. And so we get our nice green region here. So anywhere in this green region will actually be okay as far as the sort of intrusion of the second harmonic. So we can actually predict fairly well what frequency range this will be a satisfactory second harmonic termination. Not really a very broad band, in all honesty. And you can see that here, this is a slightly, well, only a slightly more complicated circuit. The same idea, I've got my colors mixed up, that should be 3.4 there. But the same idea here, you know, we're using now a single matching sort of, this is a typical, you know, matching network that one might use. So basically that's about it. You know, there are some issues which Roberto Quaglia and myself are pursuing at this time. There are issues. Obviously, we are ignoring higher harmonics. That's something we have been looking at. It does obviously complicate things somewhat. I've always felt that, you know, in class AB mode, second harmonic is the big player, you know, and so therefore it is a step, I think, an important step forward in terms of design philosophy, design methodology. Obviously, yes, class F, well, you know, I've never been a big fan of class F. This is a little slide that I show. It's another story. This is, I always think, when you're dealing with things that are current sources, you're better off staying over here in the comfort zone where impedances are low. If you make this hazardous journey over to the right-hand side, the restaurant at the end of the universe in The Hitchhiker's Guide to the Galaxy, you can undoubtedly get some good numbers here. I'm not saying Class F doesn't exist. All I'm saying is it's a very, very, this restaurant at the end of the universe is a very, very strange place to be, actually, in my opinion. I think I've already covered this whole business about zero grazing and knees. I think that certainly gallium nitride transistors the whole thing does need a bit of a revisit. So that's what I've said there. Conclusions, right? I'm down to my zero, am I now? Yeah, right. Okay. There we go. More generalized theory. I think what I'm trying to do here is to just revisit it. Obviously, there's much more detail available in the original paper. And I hope that has maybe helped some of you. Right. I think that must be my last slide because it won't go any further. Right. Okay.